This is 7.5, 7.6 part 2. We're just going to go and finish example 2 over here that we started in the first video. So we had defined angle of depression. We're starting this problem, drawing a diagram out. Mr. Efrate is watching students doing math on the second floor. He's on the second floor of Loyola, watching students doing math. Here's the line of sight that we drew. The angle of depression was said to be 40 degrees. We basically want to know how far the students are from the wall. So how far away are the students from the wall? So we're looking for this distance over here. Do we have any other information? We have 40 degrees. What else do we know about this triangle? Well, we know that the second floor is about 7 meters off the ground. So this would be 7 meters here. Now, if we were making a triangle out of this, we'd have to add Mr. Efrate's height to it as well. So that would be about 8.5 meters. 1.5 plus 7 is 8.5 meters in this triangle. Another interesting thing that we can make with this triangle is this idea here. This angle of depression is 40 degrees. We can find the angle in here by realizing that the sum of this angle, so let's call this angle theta. So theta plus 40 must be 90. So to find theta, all I need to do is theta plus 40 is equal to 90. Therefore, theta is equal to 90 minus 40, which is 50 degrees. So this angle here is 50 degrees. So I'm just going to redraw this just as a simple triangle with all the information that we have. And what we're basically doing is solving for that simple triangle. We can write a therefore statement at the end. So Mr. Efrate, 1.5 meters high on the second floor, which is 7 meters from the ground. So total height here is 8.5 meters. He's watching his students, line of sight over here, 40-degree angle of depression. The interior angle over here will be 50 because if you do 40 plus that interior angle, it should be 90. So just do 90 minus 40. And again, we're looking for this here. This makes a right angle triangle with the wall, so we can put that 90 degrees there. So we have two angles here, which is beautiful. That works out just fine. Now you can also use your angle patterns to figure out that this angle over here would have to be 40 as well. And I will post a little angle pattern review that you can go over. And you can also just do your interior angles, 50 plus 90, and then do 180 minus that 50 plus 90. That gives you 40 over here as well. So you could use your sum of your interior angles, and that would give you that as well. So let's just redraw this triangle now as a triangle that we need to solve. So here's my triangle. It's a right angle triangle. I have 40 degrees over here. Over here I have 50 degrees. Over here I have 8.5 meters. And I'm looking for x over here. I'm looking for this distance. So what information do I have? Well, I have a lot of information. We're going to use our trig ratios that involve an x over here. So let's look at x and let's choose an angle. Doesn't matter, any angle will do. I'll show you two methods to do it. Let's work with angle 40 here. So remember our trick SOHCAHTOA. X would be the adjacent side to angle 40. So we're dealing with an adjacent. Do we have a hypotenuse? No, we don't. So we can't use cos. That won't work out because we don't have the hypotenuse. But we do have the opposite side. So we can use tan. We can use tan. So we can do tan of 40 is equal to the opposite over the adjacent. So is equal to 8. Let's write down first opposite over adjacent, just so we can set it up. So tan of 40 is equal to 8.5 over x. We can multiply both sides by x, crosses x out here, and we get x tan 40 is equal to 8.5, and then we can divide both sides by tan 40 to find our x value. So x would be equal to, so let's do 8.5, make sure your calculator's in degrees mode, divided by open brackets, tan 40, close brackets. And we get about, I'm going to round to 1 decimal place, so 10.1. Let's put our little dot there to show around, to show some approximation, 10.1 meters. So this distance is 10.1 meters. And you can say, therefore, students are 10.1 meters away from the wall. So that's how you would go about and solve that problem. You just have to have knowledge of what your angle of depression is, and then draw your setup, and then make just a basic triangle you would normally see, solve that, and then put it back into the context with a therefore statement. I'm just going to show you another way you could have done this, using the other angle instead, but you would have come up with the same answer. It's a great way to verify if you have time. If you don't have time and you spend your time verifying, you're not going to have time to finish all your questions on your assignments. So let's say we decide to focus on angle 50 instead. Angle 50. How does x relate to 50? Well, x relates to 50 in that it's the opposite side. So what can we use in this case? Well, let's assume we didn't know what x was at first. So we have the opposite side. We also have the adjacent side. So again, we can use tan. But this time it would look different. We're doing tan of 50 is equal to opposite over adjacent, TOA. So tan of 50 is equal to opposite x this time over adjacent, which is 8.5. We can multiply both sides by 8.5. Cross that out, and we get 8.5 tan 50 is equal to x. And so if we put that in our calculator, do 8.5 times tan of 50, make sure it's in degrees, we get 10.1 meters. So that's another way that we could have solved this problem using the other angle. It's just the only thing that'll change is really what trig identity ratio you might be using, and also what the sides mean relative to the angles. So x was an adjacent side when you're using your 40 degrees, but an opposite side when you're using your 50 degrees. So always just look at that before you do anything. Let's go to our next question. We're going to have another definition, and then after our definition, we're going to solve the problem. So Lucas is running through an obstacle course and sees a wall he must jump over. He is 3 meters away from the wall, and his angle of elevation to the wall is 35 degrees. How high is the wall if Lucas is 1.7 meters tall? So first, let's define angle of elevation. Angle of depression was basically an angle made while looking down. Angle of elevation, as you probably guessed, is an angle made by looking up. So it's the angle between the horizon or the horizontal and the line of sight and the line of sight, sight as in looking, where you're looking, when looking up at an object. So suppose there's a person standing here. That person is looking up. This would be the horizontal line, the horizon. this is the line of sight. This angle in between the line of sight while looking up and the horizon, let's call it theta for now, that would be the angle of elevation. So in this case, we're dealing with a scenario that's an angle of elevation scenario. So let's see what we can figure out. So Lucas is running through an obstacle course and he sees a wall he must jump over. He is 3 meters away from the wall. So let's draw Lucas and let's draw a wall. So here's Lucas. Here's a wall. And we know that Lucas is 3 meters away from the wall. And he's looking up at it. So he's looking up at the wall. This is line of sight there. And we're going to draw that horizontal. And we know the angle between the line of sight looking up and the horizontal is 35 degrees because that's the angle of elevation. And then this, if you notice, that's his distance from the wall, which is 3 meters. And then we can say that this makes a right angle triangle with the wall. A line of sight and the horizontal make a right angle triangle with the wall. And what we're basically trying to figure out is how high is the wall if Lucas is 1.7 meters tall. So what you need to remember is that we're looking for this distance here. But that's just a portion of the wall, right? Lucas's line of sight looks up and makes a triangle from where his head is. Remember that once we find that x value, we're then going to have to add Lucas's height to it, 1.7 meters. So in this question, it's important to draw a diagram, otherwise you might find x, but leave out Lucas's height, and then just get a portion of the wall. So first we're going to solve for x in our basic triangle here, and then at the end, when we're done solving for x, we're just going to add that 1.7 to it to ensure that we get the whole height of the wall. So let's again draw out our triangle that we're trying to solve here. We have our angle of elevation given to us that was 35 degrees. We have 3 meters over here. We have our 90 degrees here. We could find the angle in here if you wanted to. I don't think there's a need for it right now. But if you want to, again, you could just do 90 minus 35, 180 minus 35 minus 90 and find your angle there. But let's see if we even need it. We can do SOHCAHTOA. So let's write down SOHCAHTOA. We want to find x, so we'll choose our angle that we have here. We have angle 35. How does x relate to angle 35? Well, x is the opposite side to angle 35. So we're dealing with either tan or sine. Let's see. The known side that we have is adjacent to 35. So we have adjacent, and we have opposite. So that means we're dealing with tan. So we know that tan of 35 is equal to opposite over adjacent. So we know that tan of 35 is equal to opposite, which is x, over adjacent, which is 3. We can multiply everything by 3 here to get rid of the 3. And we get 3 tan 35 is equal to x. So if we put that in our calculator, we get 3 times tan, make sure it's in degrees, 35. I'll round to one decimal place. We get 2.1 meters. So we know that the height of the wall is 2.1 meters plus 1.7. So height of wall is equal to 2.1 plus 1.7. And we get 3.8 meters. And you can write your therefore statement. Therefore, 3.8 meters for height of wall.